right, so I want to touch on just a few of the things on the review sheet that have sort of thrown people off and hopefully clarify those misconceptions before the test next week. So the first set of questions is about this graph. So this graph is showing the progress of a reaction, and this is free energy. And although we didn't really use the terminology, that can also be represented by what's called delta G. Delta means change, and G is free energy. So the first question is, what is EA? That's activation energy. We learned about that. So activation energy. What is EA with enzyme? So think of EA like this. Here is my reactants. This is A plus B turning into C plus D. And this is over time, the reaction. If you think of the activation energy as this little rock, and I have to push it to the top of the hill so it can go on its own. The distance I have to push it is the activation energy, or EA. And what enzymes do is they lower that. So with the enzyme, EA is this smaller hump. I only have to push the rock this high to get the reaction going. And by lowering EA, or activation energy, reactions can happen more easily at lower temperatures in living things. So activation energy, think of it as this hump. So with the enzyme is going to be B, the lower line, and without the enzyme is C, the higher line. Now, delta G, that's the change in free energy. So think of it this way. Look at it like a bar graph instead. Here's the amount of energy my reactants have, and here is the amount of energy my products have. The net change between those two things, that's my free energy change. And notice, because this is really important for the test, enzymes don't affect it. So the free energy change would be represented in this by arrow by D. And when you would calculate it like numerically, it would be sort of final minus initial, which brings us to this last. Is it endergonic or exergonic? So exo, giving away energy, endo, taking in energy. Well, the products contain less energy than the reactants. So this would be an exergonic reaction because energy is being given away. If you think of the energy here would be released. And in our cells, we might be able to capture that released energy with ATP and then use it to power an endergonic reaction. Now, I've never really seen them put an endergonic reaction on the AP Bio test, but what it would look like, endergonic, would be the opposite. It would look something like this. So the products contain more energy than the reactants do, like photosynthesis. It requires energy. So in the case of photosynthesis, that energy is coming from the sun. So hopefully that kind of clarifies that graph, and you can ignore all those other letters because really those are the only three things you're going to be asked. All right, so let's take a look at this second graph. So this one really throws people off. This is probably the most frequently missed concept every year on our test on this chapter. So here's what they're showing. Remember, substrate is what the enzyme is breaking down, and this is this concentration of substrate going up. So you have more and more and more substrate, and this is the rate or the speed that the reaction is going, which means higher numbers means the reaction's going faster. So if we look at this, this is the enzyme normally, or normal enzyme added, and notice this plateau here. And the question is, what's happening at the plateau? Well, what's happening is the enzymes are working at their maximum rate, or another word for this is they are saturated. So let me explain with an analogy. Hopefully this will help you understand what's happening. So here's my substrate concentration on the X, and my rate is going to be the Y. And let's just say, my enzymes are these Pac-Man things, that it takes 1 second for one enzyme to break down one substrate. So, experiment number 1, I have one substrate molecule. I have 5 enzymes waiting for it. So after 1 second passes, how much substrate will be broken down? The answer, 1, because there's only 1 there. So, with 1 substrate added, I can break down 1 substrate in 1 second. So my rate is 1 enzyme per second, or 1 substrate per second, sorry. Now my second scenario. I now have 3 substrate molecules. How many will I be able to break down in a second? Well, the answer is I will be able to break down all 3, because all 3 of these enzymes will be available, and I can now break down 3 per second. So my rate is now 3 per second. Notice what's happening in my graph. Now I have 5 substrate molecules. After 1 second passes, I should be able to break down all 5 because I have 5 enzymes. So now my rate is 5 per second. So this is my rate going up. Now I have 6 substrates, but I only have 5 enzymes. How many will I be able to break down in 1 second? Only 5. That 6th one is going to have to wait until there's an available enzyme. So with 6 substrates, I still can only break down 5 per second. That's the rate that I'm going. Now I have 10 substrates. After 1 second, how many will I be able to break down? Again, I will only be able to break down 5 because I only have 5 enzymes. Notice the plateau. Here's my plateau. So what's happening at my plateau is I'm working at the maximum rate, 5 per second. The only way I can make that plateau higher is if I added more enzymes. If I had 6 enzymes or 10 enzymes, I might be able to get a higher plateau. So hopefully this kind of illustrates where they're getting this crazy looking graph. Now let's talk about inhibitors. So what kind of inhibitor causes line A? Well, that would be a competitive inhibitor, because what happens with a competitive inhibitor, which is this picture, is that the substrate and the inhibitor are both competing for the active site. So this is going to slow the enzyme down, but the more substrate I add, and if I only have a little bit of inhibitor and a lot of substrate, this inhibitor will have less and less effect to the point where the inhibitor has almost no effect at all. So this would be a competitive inhibitor, because the more substrate you have, you can overcome this type to where it really doesn't have an effect. Now let's look at line B. So line B is showing this. This is a non-competitive inhibitor. Now, why does this one plateau lower? Well, look what's happening. So every enzyme that binds to the inhibitor, the non-competitive binds to what's called an allosteric site. And what it does is it changes the shape of the active site. In other words, instead of just slowing this enzyme down, this particular enzyme is gone. It's knocked out. It is temporarily unavailable. So let's go back to this picture. So what if I added 3 non-competitive inhibitors to scenario number 5? 1, 2, 3. Now, what's the max rate I can do? Oh, I can now only break down 2 substrate molecules per second. I can't break down 5 per second anymore because 3 of my enzymes have been deactivated. So now my plateau would be down here at 2. If I knocked out 4 of my enzymes, my plateau would be even lower. So with non-competitive inhibition, you're basically removing some of your workers, and so your maximum rate, Vmax, or the max rate that the enzyme can go, is going to be lower. Now that plateau can be in different places. There's no reason it has to be exactly here. This must mean maybe they added enough to knock out about 50% of the enzyme. If they added more, it might be down here. If they added less, it would be here. But the bottom line is, adding more substrate doesn't change it. It plateaus. It never meets that first line. So hopefully that explains the saturation graph. The other thing I want to explain is this one. So this graph is, if you were to graph this, you would also get, let's just say you started with 7.0 millimoles of substrate. So over time, that 7.0 millimoles would get broken down into products. So at 60 seconds, maybe you're at all 7.0 broken down. And if you were to keep going past 60 seconds, this number is not going to get any bigger. So let me show you what this looks like in a graph as well. So here is, I added 10 substrate molecules, just 10, to this beaker. And they're the red dots. And this is my enzyme. I just added one drawing of an enzyme. So at time 0, when I start, I haven't made any product yet. I just have substrate. Now, after 1 second, I have now made 1 product, and I'm down to only 9 substrate molecules. So notice the blue one. At 6 seconds, I now have 6 products and 4 substrate. But notice, since I'm doing this in a beaker, there's nothing going on to take away the product. So what's happening now is it's becoming harder for the enzyme to bump into the substrate because the product is getting in the way. At 10 seconds, I only have 2 substrates left, here and here. Will the enzyme break them down? Sure, but it may take some time before that substrate randomly ends up in the right spot because you have all this product in the way. And eventually, you've made all 10 products at 15 seconds, and if you were to check at 20 seconds, you would still be exactly the same because there was only 10 substrates. So once you get to 15 seconds, it's going to flatline. This is not saturated. What's happening in this graph, this is the amount of product being made over a period of time. And what's happening is, at first, the enzyme works really fast, but it's starting to slow down because it's running out of substrate. The reaction is ending, basically. And eventually, this flatlines because the reaction is over. There's no more substrate left, or it's reached what we call equilibrium. There's nothing for the enzyme to do. It's like all your friends showing up to work on a project and you already finished the project. There's nothing for them to do. This is the opposite of saturated. Saturated is when the enzymes are working at their max. Now, if you don't understand the concepts, theoretically, you could just memorize it. If it's amount of product over time, the flat line means the reaction is finished. It's at equilibrium, it's over. If the graph is substrate concentration and rate, then this is going to be saturated because it's working at its maximum rate. I really hope you understand the reasoning, but just to comment. So the rate, remember, for the test is going to be amount 2 minus amount 1 over time 2 minus time 1. So for this one, it ends up being 0.25, and your units would be millimoles per second. And then for 40 to 50 seconds, it ends up being 0.03 millimoles per second. And the reason it slows down is, again, because this reaction is ending. It's reaching equilibrium. You're basically running out of substrate. Everything's been converted to product, so there's not going to be anything for the enzyme to do. So the enzymes, they're not shut down, there's not an inhibitor, and they're definitely not saturated. So make sure you know that. Last quick comment. So for graphing, so in this experiment, really quick, if you recognize, you don't need the test tube number. They were looking at temperature and amount of product. Make sure when you do this, you label your units. Temperature, that's your independent variable. That's what they were changing. And then your amount of product, again, make sure you include this. And then I will take off points. It needs to take up at least half of the axis on each thing. So your graph should not be this, or I'm going to take points off. It doesn't have to fill the space perfectly. I realize that, it's hard to make a scale that perfectly fills every box. But you should get something like this when you graph this. Make sure, remember, you don't go beyond the first and last points, whatever they are. You can make a dotted line, that's okay. The optimum temperature for this ends up being, when you graph it all out, and I do have the key to this worksheet online, 25 degrees Celsius. The independent variable is the temperature, the dependent is the amount of product made, and really important, to predict what you would get at 40, any answer that would be acceptable, you figure here's 35, here's 45, your answer should be somewhere between those two numbers, and you can basically estimate it from your graph, between here and here. And at 70, again, anything below 0.2 would be acceptable because that would be, but it's very likely it would be 0. It cannot be a negative number. If you people were putting negative numbers, you can't make a negative amount of product. The least amount of product you can make is 0. And last but not least, a negative control group. So this is really important because I've seen this come up on the AP exam many times. Anytime they do an enzyme experiment, the control group is going to be that they're either going to add water instead of enzyme. They still have the substrate, but they add water instead of the enzyme, or they use boiled enzyme. Because we know that boiling, it denatures it, so that would be just the same as adding no enzyme at all. So they would do one at 25, like they have here, because that ends up being their optimum, but do it with no enzyme. Why? Why no enzyme? Why not no substrate or whatever? And the reasoning is because, remember, enzymes just speed up reactions. If we do one at 25 degrees Celsius with no enzyme, we can see what the rate of the reaction is on its own without enzyme present, because theoretically the reaction should occur on its own. It may just be so slow that it's negligible, but this would give us a comparison. So that's what you'd want to see, is either water or boiled enzyme. That's a really, really common one on there. So if you see that, that there's a group with boiled enzyme, that's what it is. It's your negative control, because you basically want to see what happens without your independent variable, which even though technically your independent variable here is temperature, but it's the effect of the enzyme at these different temperatures. So hopefully that clarifies. And again, the worksheet key is online. So good luck with your studying.